Chapter 15 mostly focuses on combustion. So I'm doing a little bit more in environmental chemistry thermodynamics than the thermodynamics from the book. So for the exam and for the homeworks, really rely on the notes from class and the class lectures rather than the textbook. So are there any questions about anything before we get started? Okay, then I'm going to go ahead and get started. So last class we were discussing enthalpy of reaction, enthalpy of formation. We did a quick example problem. So we are going to be continuing with that. And I'm going to start with my notes here. All right. So some of you have hopefully seen this before in chemistry, but I am not relying on your chemistry knowledge, and I will show you again how to do it. So when we're looking at getting the overall enthalpy of a reaction, we have something like, for this example problem, we have 1 mole of a compound A plus 1 mole of a compound B reacting to form 1 mole of a compound C. So something really generic, really simple. A, B, and C can be a bunch of different chemicals. I'm trying to just make this as universal as possible. And then you're asked for this problem, find delta H at standard temperature and pressure of this reaction. And then you would be given something like, given the first equation here, 2 moles of A plus 2 moles of D react to form 4 moles of E plus 2 moles of F, and their delta H at standard temperature and pressure value is some positive value of X. You're also given a second equation, 1 mole of C plus 1 mole of F react to form 2 moles of G and 1 mole of B. And these have some sort of positive value Y. And a third equation where 1 mole of E plus 1 mole of F react to form 1 mole of G plus 1/2 mole of D. And these have some positive value of Z. So as I was saying before, these are very generic, right? These can be a bunch of different chemicals. I'm just trying to make this as like conceptual as possible so you can apply it to a wide range of products. I'm trying to pull up the chat and it does not like to cooperate. There we go. All right, so make sure to use the chat if you have any questions or if you need me to slow down or anything. Okay, so we have this starting equation. We have these given equations with their enthalpy of reaction values that are given. So we need to use these equations to form this equation. That's our overall goal. So we want to combine some sort of combination of these equations to make this final equation of 1A plus 1B goes to 1C. So the first thing that we're going to do is we know that we need our final equation of 1A plus 1B plus 1C. So we're going to look and see where we can get I'm going to start with this A term. So I'm going to start with my A term. I'm going to look for getting 1A on the left side of my equation. So I'm going to look through these equations. What equation has an A? There's only one equation that has an A at all, and it's already on the left side of the equation. So I have the equation 2A plus 2D goes to 4E plus 2F with a delta H of positive X, H at standard temperature and pressure. So the difference between, I'm looking for 1A, I have a 2A here, so I'm going to need to divide this entire equation by 1/2. And so then I would end up with my 1A, which is what I want, plus 1D goes to 2E plus 1F. And my delta H here is 1/2 X. So I have my 1A isolated. Now I'm going to move on to my 1B that I need. I guess I shouldn't check that yet. I didn't do it yet. So I'm going to look around. I have a B here, and I don't have a B anywhere else. So I'm going to use this equation, but the B here is on the right side of the equation, so I'm going to need to reverse the equation. So I have 1C plus 1F goes to 2G plus 1B with my delta H naught is equal to positive Y. And I'm going to need to reverse this reaction to isolate my 1B on my left-hand side of the equation. So therefore, I would have 2G plus 1B goes to 1C plus 1F. And my delta H naught is going to be the reverse of positive Y, which is negative Y. Then I'm going to look for my third chemical of interest, which is 1C. So I have a C here, and I don't seem to have a C anywhere else. So I already have my correct C on the correct side that I want. So I already have my 1C that's isolated. But when I okay. So I already have my 1C, so I'm not going to need to deal with my 1C here. This equation up here took care of my 1B and my 1C, which is nice. But then I still need to do another consideration for this third equation. So I have an A, a B, and a C, but I also have these additional chemicals that I don't want in there. So right now I have a D, E, and an F, and a G. So my F's are, I have two F's on this side. I need two F on this side. Right now I only have 0 F's. I have 2 E's on my right-hand side. I have 0 E's on my left-hand side. So I would need 2 E's on my left-hand side. And I have 2 G's on my left-hand side. And I have no G's on my right-hand side. So I would need 2 G's on my right-hand side to cancel out. Does that make sense? I think it'll make more sense when I work through it. So what I need to do here is cancel my E, F, G, and D. This equation is pretty simple because I can cancel those all with this one equation down here, where I have my 1E plus 1F going to 1G plus 1/2 D with my delta H of positive Z. And so in order for me to get rid of this 2E, these two F's, I have 1E and 1F. So right now I think I need to multiply by 2. I also need to get rid of this 1D. And I need to get rid of this 2G. So if I multiply this equation by 2, I would have 2D, 1D, or 2G, 1D. So that seems to make sense. So I need to multiply this by 2. That should cancel everything that I need to cancel. So therefore, this equation becomes 2E plus 2F goes to 2G plus 1D with a delta H at standard temperature and pressure of 2Z. Positive 2Z. Okay, so now I have the equations 1a plus 1d goes to 2e plus 1f. And my delta H of formation here is 1/2 of x. And then I have 1b, I'm just rewriting what I did before, plus 2g goes to 1c plus 1f with a delta H of negative y. And then I have 2e plus 2f goes to 2g plus 1d, and I have 2z as my delta H. So now I can cross out anything that's balanced between the left and the right side. So I have 1d here. I can cancel it with the 1d here. I have 2f's here, 1, 2. I can cancel it with the 2f's here. I have 2g and 2g. And I have 2e and 2e. So overall, this leaves me with 1a plus 1b goes to 1c. And my delta H is going to be the summation of all of these, 1/2 x minus y plus 2z. So you need to multiply and reverse your different enthalpy reactions to get you to your overall starting chemical equation that you are interested in. On Friday, we're going to work some problems during the problem solving session where you will do this with actual numbers. Okay. All right. Okay. So I'm going to have you work an example problem where we have the combustion of propane gas. So propane gas is C3H8 in the gaseous form. It's reacting with oxygen. And that's what combustion means, is a fuel is reacting with oxygen to produce energy. And this yields carbon dioxide as a gas and water as a byproduct liquid. So we're going to do what I was just doing before, but first I want to give you some values. So we have given, sorry, I'm changing the problem around. So we have these equations. The formation of propane, so CH8 as a gas, can become 3 carbon as a solid plus 4 hydrogen as a gas. What's the state of oxygen here? What's the state of oxygen ever? Sorry, it's always a gas. Especially for combustion, it's always a gas. Actually, I want to write this in the reverse, this equation. Sorry if you already started writing, please erase it. So this is the way that we can make propane gas is by reacting solid carbon with hydrogen gas and form propane as a fuel source. And the delta H for this equation is going to be the delta H of formation for propane, which is gotta look it up in my table. Negative 103.85 kilojoules per mole. Then we have a second equation here where we have 3 carbon as a solid, or I'm sorry, just 1 carbon as a solid. 1 carbon as a solid plus 1 oxygen as a gas reacts to CO2 as a gas. And this delta H here is going to be the delta H of formation of carbon dioxide, which is negative 393.5 kilojoules per mole. And finally, we have um, 4 moles of, nope, don't do 4 yet. We have hydrogen dioxide or hydrogen gas, H2 gas, reacting with 1/2 of oxygen gas to go to water, form liquid water. So this is going to be our delta H is the enthalpy of formation of our water, which the enthalpy of formation for water is negative 285.8 kilojoules per mole. Okay, so we want to find the delta H of this reaction. This reaction being the combustion of propane. Combustion of propane. So if any of you have a propane grill, this is what is producing that energy from that grill. The heat and energy. So I'm going to give you a few minutes to try to solve this. Remember, you have to kind of balance the equations, reverse them, multiply, balance them out, cancel, add together your delta H's, and get your total delta H. So I'm going to let you work on it for a few minutes, and then we will review. No, I would try again. You're off by over, it should be at over 2 times that amount. Yes, Elizabeth. Yep. Okay, so just another minute. I know some people are already finishing, so just another minute or two. Yeah, that's the tricky part. Or not tricky part. That's just what you have to check every time. Okay, so the very first thing that we always need to do for a problem is to make sure that our original equation is balanced. This one is not balanced. It needs to have 1 mole of propane reacting with 5 moles of oxygen to form 3 moles of carbon dioxide and 4 moles of H2O. So therefore, we know that this equation that we're looking for by combining these actually looks like this. So you can do it a variety of different ways, whatever you're most comfortable with. If you've been taught another way, please do whatever you like. You don't have to do it my way. But the first thing that I would do is I would start with that 1 mole of propane gas. So I know that I want my 1 mole of propane, my 5 moles of oxygen reacting with 3 moles of carbon dioxide and 4 moles of water. I know that this is the equation that I want. So first I'm going to start with this 1 mole of propane. And the way that you can get that is by looking at your enthalpy of formation of propane. So if we look at this equation here, we have 1 mole of propane, but it's on the product side instead of the reactants. So we would need to reverse this equation. So this one needs to be reversed, but we don't need to do any multiplication. So this equation would become 1 C3H8, 1 mole of propane goes to 3 solid carbons plus 4 hydrogen gas. And the delta H here would become the negative delta H of formation for propane, which would be positive 103.85 kilojoules per mole. But we have 1 mole, so it's really just kilojoules. And then when we look at our next equation, the equation 2 has both carbon dioxide and oxygen. So this is going to be focused on in equation 1. We're going to focus on these two in equation 2. So looking at this one, we want 5 moles of oxygen on the left side and 3 moles of carbon dioxide on the right side. So that's obviously, it's not going to work if we multiply everything by 5 or multiply everything by 3. So this kind of gives us a hint that there's probably another equation that includes either oxygen or carbon dioxide. So now we need to look around for those. So the only carbon dioxide I see is in equation 2. But for oxygen, I do see that it is included in another equation. So when I look at the oxygen that's included here, I know that I can make a consideration for this oxygen later. So I'm really going to rely more heavily on my smaller number and the one that is only represented in this one equation. So that means that I need to be looking at 3 moles of carbon dioxide, and I'm going to need to multiply this by 3. I'm not going to need to reverse the equation because I already have oxygen on the reactants, carbon dioxide on the product side. So when I multiply that by 3, I get, so this is for oxygen and CO2. When I multiply that by 3, I have 3 moles of carbon solid plus 3 moles of oxygen gas, resulting in 3 moles of carbon dioxide gas. And my delta H here, I need to multiply by 3, which is going to give me 3 times negative 393.5 kilojoules per mole. Or if we type this in our calculator, it's roughly 1200. I didn't remember to write down what I got, 393.5. So 1180.5 kilojoules per mole. But we already, this 3 is kind of a representation of our moles. So we have 1 mole here, we have 3 moles here. So actually this is really just kilojoules, since this is 3 moles. So we can make this just kilojoules. And this one's for 1 mole, so just kilojoules. All right, so for the third equation, we have our water that we're dealing with. So this one's going to be in our third equation. We also have a little bit of this oxygen that we're still considering from our third equation. So here we have oxygen. We need to make sure that we're adding at least 2 oxygen because we already have 3. We need to get 5. And then we need to get 4 waters. So we need 2 oxygen, we need 4 waters. It would make sense to multiply this entire equation by 4. Because then we have 4 waters, 2 oxygen. So that gives us what we want. We don't need to reverse it. So then we come over here, and here we have oxygen again and water. We're going to multiply it all by 4, which gives us 4 H2 gas plus 2 H2 goes to 4 H2O liquid. And the delta H here, we multiply by 4, which gives us 4 times negative 285.8 kilojoules per mole, which gives us 1,143.2 kilojoules. And when we look at adding this entire equation together, we have our 3 solid carbons that cancel. We have our 4 hydrogen gas that cancel. We have nothing else that cancels, but we have these 2 waters that we'll add together. So we have 1 mole of propane plus 3 plus 5 moles of oxygen gas. Sorry, propane's also a gas. Going to 3 moles of carbon dioxide gas plus 4 moles of H2O as a liquid. So this equation should directly match your starting equation. Otherwise, you need to have either an additional reaction equation or you need to check your math. Check that your balance, check your math. And then my delta H here is going to be 103.85 positive plus 1,180.5 plus 1,143.2 kilojoules, kilojoules, kilojoules. And this gives us, oh, I'm sorry. These are negative. Yeah, these are negative. So, yeah, so 103.85 minus 1,180 minus 1,142 gives you roughly minus 2,220 kilojoules of energy from this combustion of propane gas. So is this exothermic or endothermic? Yes. So this is exothermic. Is this releasing a large amount of energy, a medium amount of energy, a small amount of energy? Like how is this, negative 2,000 kilojoules? Is that a lot, a little, you don't really know? Yeah. So this is releasing a lot of energy. So minus 2,000 kilojoules is releasing a lot of energy. That's why we do combustion reactions. They're always going to be higher. So as like a logic check for yourself on an exam, if you're asked to do a combustion reaction, you should have a pretty high negative delta H value. That's just the nature of combustion reactions.
So would it be endo if it was negative and really tiny?
Nope. The only way it's endothermic is if it's positive.
Okay.
But if it was really tiny, it would be like slightly exothermic, but it would still be exothermic.
Okay.
Yeah. Other questions? Okay. So one of the things that we were applying, but I haven't really named yet, is this the additive nature of enthalpies is considered to be Hess's law. If just in case, I'm not going to test you on like what it's named, but just in case you've already seen that in your classes or something before. So Hess's law is where you have your change in enthalpy of reaction at a standard temperature and pressure is going to be additive of your change in temperature. I'm sorry, your change in enthalpy of your additive equations. So this is called Hess's law. The overall change in enthalpy of a reaction is the additive summation of the change in enthalpies of your individual reactions that are occurring. Okay. Another thing to note is this reaction represents the formation of propane. This reaction represents the formation of carbon dioxide. This reaction represents the formation of water. So this is how we're forming these chemicals. So I didn't need to look up any sort of equations or anything to get these delta H values. I just looked these up as their standard enthalpy of formations.
Just asking, would we be given the delta H values for each equation, or would we have to like check them out?
So you will be given tabulated delta H values, or you will be given delta H values in the problem statement. And I don't expect you to memorize like what's forming propane. And I don't expect you to memorize, like you should probably memorize what's making water, right? Carbon dioxide, or I'm sorry, hydrogen gas and oxygen gas can make liquid water, but I don't expect you to memorize any of those. So they would be provided for you, the like step-by-step intermediate equation. Other questions? Okay. Then let's do another example. So here's another example problem. For this reaction, the combustion of 1 mole of ethanol, combustion of 1 mole of ethanol. So we have ethanol C2H5OH as a liquid reacting with oxygen, forming carbon dioxide and liquid water. So when you see the word combustion, you always have some fuel reacting with oxygen to form CO2 gas and water. Always. This is the exact same one we did before with propane. Combustion always follows this exact equation. So we are reacting some organic carbon fuel with oxygen to form heat, energy, and byproducts of carbon dioxide and water. So in here, we also have heat and energy. Even heat is energy. So I guess heat / energy. That's always combustion forever. So we have combustion of 1 mole of ethanol given by this equation. And we have the standard enthalpy of formation for propane, I'm sorry, for ethanol, C2H5OH is negative 277.7 kilojoules per mole. For oxygen, this is an element, so it's 0. For carbon dioxide, we have negative 393.5 kilojoules per mole. And for water, this is an element, no, it's not an element, sorry. Water, it's not elemental, it's a compound. We have negative 285.8 kilojoules per mole. Keep in mind that this is the enthalpy of formation. So forming carbon dioxide, forming water, which is what we did here, right? So forming carbon dioxide, forming water. These are the same values. And then forming propane. So this is similar to the last problem we did. I'm just giving you another shot at it. So work it for a couple minutes, type in the chat once you get a value for find delta H of the reaction, assuming standard temperature and pressure. So type in the chat once you get a number. So Kat, I would try again. You're off by like 500, 600. No, Connor, it's like half of that. So I'm going to go ahead and start working on it unless anybody wants more time. I might have kind of been unintentionally tricky. I probably should have given like a warning. Yes, Kat. Yeah. So did you work it the way that you worked the last problem, Kat? Or did you work it another way? Okay. So you worked it similar to how this worked, right?
Again, and I realized I have products reactive. Probably should.
Yes. Okay. Emma, did you work it this way as well?
I think so. I didn't like I got a positive number, so that's the only thing I did wrong. But I like balanced the equation first and then I just added this stuff.
Okay. But then you got like 1,367. Okay. So you can work it either way. You can work it by looking at those formation equations, the formation of ethanol, the formation of carbon dioxide, the formation of oxygen, just like we did here, and doing this step by step to get these products. Or you can do it even simpler and remember that we have the formation, the change in enthalpy of a reaction is equal to the summation of mass times the change in enthalpy, of our change in enthalpy of formation of our products minus the mass times the change in enthalpy of formation of our reactants, which is really just like the enthalpy of our products minus the enthalpy of our reactants, which you've probably seen in chemistry before. So the very first thing that you need to do is balance this equation always. So once again, we have 5 oxygen, 3 carbon dioxide. Nope, sorry, that was another problem. 3 oxygen. You have 3 oxygen, 2 carbon dioxide, and 3 water to balance this equation. So 2 carbons, you have your hydrogens, so 6 hydrogens, 6 hydrogens. Then you have 7 water or 7 oxygen, 4 plus 3, 7 oxygen. So balance the equation. And then we.
Wait, I'm sorry.
Yeah.
Wouldn't it be for the oxygen? Wouldn't it just be 1 because there's already 3 oxygen, like 1 in the C2H5OH and the O2?
So we have 1 oxygen here, and then we had another 2 oxygen here, which
Yeah.
means that we would need to balance those, but we first needed to balance the carbons. So we need to put a 2 in front of this carbon dioxide. So we first balance this carbon, so we need to put a 2 here, which makes this side have 4 carbon dioxide, or I'm sorry, 4 oxygen plus another one, 5 oxygen. So now on this side, we have 3 and a 1. So in order for us to get 5, there's no real like good way to do that. And we also have 1 hydrogen on this side, but 2 on this side. So we need to figure out a way to balance the remaining hydrogen and oxygen. And the easiest way is to put a 3 in front of your water here. And then, I'm sorry, you have 6 hydrogen. So that 3 here gives you that 6 hydrogen. So now you know for sure you have to have these 4 oxygen plus this 3 oxygen. And so you know you have 1 here, 2 here, so 3. How do I get that to equal 7? Well, put a 3 here. Now you have 6 plus 7. Does that make sense?
Oh, okay, yeah.
Okay.
Thank you.
Sorry, I kind of explained that sloppy, but the first thing you have to do is balance your carbon, and then you balance your hydrogen, and then you have to figure out how to balance your oxygen at the end. Okay. So now that I have this equation, I know that my delta H of reaction at standard temperature and pressure is going to be equal to 2 times the enthalpy, the standard enthalpy of formation change of carbon dioxide, plus 3 times the standard enthalpy of formation change of water, minus, so these are my products, right? Products. Minus oxygen has a standard enthalpy of formation of 0 because it's elemental. So really only this standard enthalpy change, 1 times the standard enthalpy change of formation of my ethanol. So this equation becomes 2 times, for carbon dioxide, we have negative 393.5 kilojoules per mole, but this is 2 moles, so that'll cancel out, plus 3 times this formation of my water, negative 285.8 kilojoules per mole, and then minus negative 277.7 one mole of negative 277.7 kilojoules per mole. So these moles are going to cancel because we have 2 moles, 3 moles, 1 mole. And then we're going to have here negative 787 kilojoules minus 857.4 kilojoules minus negative 277.7 kilojoules. So this is 1,644, negative 1,644 kilojoules plus 277.7 kilojoules, which equals minus 1,367 kilojoules. Beefy is snoring. Okay, so this is, you can work it both of these ways. You can either use your equations, reverse them, multiply them, cancel them out, add your enthalpies of formation using Hess's law, or if you have your enthalpies for these products and your reactants, you can do the enthalpy of the change in enthalpy of the reaction at standard temperature and pressure is equal to the change in enthalpy of your products minus the change in enthalpy of your reactants. You have to correctly balance your equation, and you have to include those mole values. And you also need to have information for all of your products and reactants. So any questions about that? Okay, then let's do one more and we'll be done for the day. So we have calcium carbonate reacting to form calcium oxide and carbon dioxide. So calcium carbonate, CaCO3, which is a solid, and it's going to react to form calcium oxide, which is a solid, plus carbon dioxide, which is a gas. So the standard enthalpy of formation for, the standard enthalpy change for the reaction of this equation is 178.1 kilojoules. So endothermic or exothermic?
Endo?
Endothermic?
Yep, endothermic. So it is absorbing heat. And we want to calculate the standard enthalpy of formation of calcium carbonate solid given CaOS, calcium oxide, and carbon dioxide have a standard enthalpy of formation value. And we're assuming this is all at standard temperature and pressure. These values are negative 635.5 kilojoules per mole for calcium oxide. And then for carbon dioxide, I just wrote it before, but now I'm looking it up again, negative 393.5 kilojoules per mole. As a note, I'm looking these up in a table, but tomorrow on Friday, I'm just giving you the table. So they won't be given like this. You'll have to look them up from the table yourself. Okay. And then we want to find calcium carbonate. So I'll give you a couple minutes to work that and then I'll go over it. Okay, so it seems like some of you have the answer. So yes, one thing that you could do is you could Google enthalpy of formation of calcium carbonate, and that's what you get. You can also look it up in the same table that I looked up these values in. But for this problem, it's probably better to practice the material. So we have our change in enthalpy of reaction at standard temperature of pressure is going to equal the summation of the enthalpy, change in enthalpy of our products minus the change in enthalpy of our reactants. So here our products are calcium oxide and carbon dioxide. So here we have, well, I'm sorry. I should have started at the beginning. First, we need to make sure our equation is balanced. We have 1 calcium, we have 1 carbon, and we have 3 oxygen. So the equation is balanced. That's why I just skipped over that. That's my fault. So the summation of the change in enthalpy of formation of our products is going to be calcium oxide and carbon dioxide are our products. So this is going to be 1 times negative 635.5 plus 1 times negative 393.5. These are in kilojoules. And then minus my reactants, which I am trying to figure out. So you can write this however you want. You can make it X. I'm going to make it CaCO3 solid as my enthalpy of reaction formation. And these are all going to be equal to the change in enthalpy at standard temperature and pressure of my reaction, which I was given to be 178.1 kilojoules. So then it's just math, right? Plugging and chugging. So you're going to have like negative whatever, 1100. You're going to change this to this side. So it's going to be about you're going to move this to this side, which is going to give you positive 1207.1 is equal to negative formation of calcium carbonate. So then moving the negative to the other side, this is negative 1207 kilojoules per mole is equal to the enthalpy of formation of calcium carbonate solid. So for every one mole of calcium carbonate solid, we have negative 1207 kilojoules. You can confirm your answer by looking this up in the table, and this is also what's tabulated. So that's great. Oh, he's gonna stop. Oh, do you see he's dreaming? His little feet are running and he's like barking at something. And then he's so cute. Oh, he's so cute. He kills me. All right, so that's the last thing that I was gonna have you practice today. So anything that you have any questions about? Okay, well then the last thing before we go, I'm using a chemistry book right now, not the thermo book, and they have a few like, they have a table that I think is kind of fun. You don't have to use this table, but I'll just use the information from it. Okay, so which of these 3 do you think have the highest fuel value? So kilojoules per gram, carbohydrate, fat, or protein. So the highest fuel value. So if you were to like burn these, what gives you the highest fuel value? Interesting. There's not a consensus. So your highest fuel value between carbohydrate, fat, and protein is fat. So you have 38 kilojoules per gram for fat, and carbohydrate and protein have 17 kilojoules per gram. This is why, you know, if you're like stuck without food, you want to have a good layer of fat because that gives you the most like fuel value to burn. Or if you need to make your own candle or like food source or something, like fat. It's always the best way to go. Just imagining how well blubber was burned. Yeah.
Yeah, sorry, I don't know if you know what I'm talking about. Like they used to use like whale blubber for like lanterns or whatever.
Yeah, exactly. Like Shackleton, who was like stranded in Antarctica, they use like seal and whale blubber all the time for like food and candles and everything. Yeah, so fats have the best like fuel value. And then also, okay, which do you think out of these three has the best fuel value? So kilojoules per gram, they're hiding like energy per gram between apples, beer, and bread. So kilojoules per gram, which has the best fuel value, the best like energy value? And like apples, beer, or bread? All right, I have two guesses. Beer's like diluted bread. Yeah, I mean, like from a yeast perspective. So, bread. Most people seem to agree on bread, which bread makes the most sense, right? Kilojoules per gram. That is the answer. But one thing you didn't consider was that beer has ethanol in it. So actually, as a fuel source, I thought all of you would say beer, right? Because it's like 3.5 to like 5% of ethanol. When you look at alcohol in a person's body, it's converted to ethanol. So I thought all of you would be like, oh, beer for sure. But it is bread at 12 kilojoules per gram. Beer's at 1.8 kilojoules per gram. I think it's because it's mostly water, but there is ethanol in it. Okay, and then last question. Oh, this is a tricky one. Okay, this one's hard because these are all like high. Which has the highest fuel value according to the book between cheese, fudge, like chocolate fudge, and a hamburger and peanuts? Cheese, fudge, hamburger, and peanuts. Cheese, fudge, hamburger, and peanuts. And we're looking on a kilojoule per gram basis. All right, so two votes for cheese. Cheese, fudge, hamburger, and peanuts. All right, so now we're spreading out our guesses. Okay, so last place is a hamburger at 15 kilojoules per gram. Burger, yeah. Yeah, 15 kilojoules per gram is last place. Third place is fudge at 18 kilojoules per gram. Second place, between cheese and peanut, dun, 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 is cheese at 20 kilojoules per gram. And then highest is peanuts with 23 kilojoules per gram. I think it's because they have like, they're like such dense little fuel sources, right? Like peanut oil, I guess. Yeah, like peanuts. And then just for our last fun fact of the day, eggs have 6 kilojoules per gram of fuel. So go eggs. Okay. And this is mostly because out of what I named, cheese and bread or cheese and peanuts have the highest fat content. So that's why they are the top two. And the fat content of peanuts is just a little bit higher. All right, so, there you go. That's fun. Fuel your body using thermo and enthalpy and pholon, et cetera, et cetera. So on Friday, we're going to do some more of these problems using enthalpy equations, change in enthalpy of formation. I will be doing in class like usual, and then also on Zoom. So I will see you all on Friday if you don't have any questions. And please, review the notes, make sure you understand what we're talking about, read the chapter in a loose way, just kind of skim it. It goes way more into combustion kinetics and fuel ratios than we really need to. So any questions before we go? Yeah, everybody bring your pets to class. We had dogs and birds today. So
Thank you.
good birds, Layla. All right, I'll see you on
Thank you.
Friday. Have a good rest of your day.
Yeah, have a